Hi all, this is Mr. Yeager. Today we are looking at what are called elevator problems. All right. So these problems are going to be sort of the connection between this unit, which we're describing initially looking at force, to looking at more dynamic situations where the object is really moving around in different directions and what that does to the different forces acting on the object as well. So we call these elevator problems, or sometimes called apparent weight problems. There's two names to them, but it's the same idea. Okay? And so what we're looking at here is really the situation of any object being pulled up or dropped down. So we usually look at objects in an elevator. Okay? We look at you acting in an elevator. What happens to you? How do you feel in that elevator as it accelerates up or as it accelerates down? Okay? As it goes faster upwards or actually goes faster downwards. All right? And so if you've ever been in an elevator, you have felt this before. Okay? And a really fast-moving elevator, that's the thing. Slow-moving elevators don't work very well, but in a fast-moving elevator, when it starts going, what you feel is basically, if it starts accelerating upwards, you'll feel like you get pushed down. Okay? You'll feel that as your body gets pushed down into the elevator itself. Okay? You almost feel like that you weigh more. Your body gets shoved more into the elevator floor as the elevator starts accelerating upwards. Okay? So you feel heavier, is what we say. You feel heavier as you accelerate upwards. Okay? On the other hand, if you're in the elevator and maybe you're about to go down, okay? Sorry, I'll draw that guy again here. As you go down the elevator, okay, as it falls, supposedly connected to the cable, we don't want it to be completely falling. But as it goes down, what happens is you actually feel a little bit lighter. The ground is leaving you. All right? It's actually falling faster than you. And you will feel lighter. All right? Is what you're looking at here. So when it accelerates up, it feels heavier. As it accelerates down, you'll feel a little bit lighter. What I've done with my sons in the elevator sometimes is we jump right at the very beginning, and it's like you actually get a little bit higher. Same thing works for any ride, any fair ride or park ride, like at Disney World, where it shoots you up or drops you down real fast. When you get shot up, you get pushed into your seat more. All right, like this example over here. Or when you get dropped, it's like you're falling out of your seat. So that is what we are looking at. And again, we look at this idea that you feel heavier or feel lighter. That is what we're going to call your apparent weight. All right? So let's look at the difference between apparent weight versus weight. Okay? Well, the thing is with weight, all right, it doesn't change. There is no change to your weight. We're not talking about going to another planet. We're not talking about the difference between weight and mass. We're looking at two different types of weight. Okay? Apparent weight versus what I can call real weight. Your real weight is equal to m times g. It's what we've been solving for all the time in this unit so far. All right? So even though that elevator moves down, this doesn't change. You're still mass, you're still gravity. The gravity's still acting on you. The Earth is still acting on you the same. It's still going to pull you down. So your weight is whatever it is. But as I just stated, with your apparent weight, as you accelerate upwards, we said you feel heavier. And it's actually proven that if you happen to be standing on like a bathroom scale, okay, or a doctor scale, when you accelerate upwards, you'll actually see your weight increase, or you'll think your weight increases, okay? It appears that your weight increases. All right, that's the key. Does it actually increase? No. No, you're still m times g. But what's happening is there's now another force acting against your weight, adding to it, and so therefore you appear to be heavier. Vice versa, if you're standing on a scale and it accelerates downwards, it'll appear on that scale that your weight decreases. And so why is that happening? Why, it's not actually changing, but why does it appear that your weight is changing? And it's because a scale that you stand on actually measures the normal force. All right? When you stand on a scale, very large scale, you push down on the scale with your weight, and it pushes back up. And that would be the normal force. It's actually reading the normal force because if you decide that you want to push down harder, you should actually see that reading change. And that's because it's the normal force that it's actually reading. How much is it actually having to push back up on you? Okay? And so that leads us to how we solve these particular problems. Okay? We're going to focus on the elevator idea. What they're going to talk about is you're in an elevator, and it's either moving up or down, velocities are up or down, and you either have an acceleration up or down, or no acceleration. We'll look at that too. So you basically have this situation. Are you moving up or down? Are you accelerating up or down? Again, acceleration does not mean that you're moving. All right? It does not mean motion. It's how your motion is about to change. All right? So, if this is the situation we're looking at, let's think about the free body diagram that you're going to have. Weight down, normal up. Pretty simple with free body diagram. No applied, no left and right forces. So if I said, okay, please write me out a net force equation for this. It would be net force equals m times a, which would equal n minus w. Or it could be F net equals m times a, which equals w minus n. Huh. How do I know which one, which one should I use here? Should I use n minus w or w minus a? Okay. How do I know when to use each one? Well, it's actually fairly simple. The way you know which formula to use is when you know the direction of motion. The direction of motion will tell you. The velocity will tell you. We will say, and this is a very, very important rule, okay? Follow this rule for this unit and into the next. We will say the direction of motion is always positive. Okay? So what we mean by that is, this is very important. All right? The direction of motion is always positive. All right? What we mean by that is, if you're in an elevator, okay, and the elevator is moving up, any force pointing upwards will be considered positive. Any force pointing opposite to the direction of motion will be considered negative. So I'd write this version of the problem out as n minus w. It's the velocity, not the acceleration. Be very careful with that. The acceleration, we're going to follow the same rule. Okay? The forces in the direction of motion will be considered positive, opposite, negative. And so therefore, if you're in an elevator that's moving down, we will say net force is equal to W minus N. If you follow these rules, you don't have to worry about the sign for G. G will always, just plug in G always as 10. Don't sit there and go, should I make it negative? No, no, no. If you follow these rules, I'm taking care of that for you. So just plug it in as it, write in minus mg, and write in both of these as positive numbers. This right here, mg, positive numbers. Okay? Don't mess with it. What you're going to be solving for is for the normal force. We're looking for the normal. The normal is the apparent weight. It's the scale reading. It's what it's going to say. All right? So therefore, if we try out a problem here, let's say you're in an elevator, it's moving up, and it's accelerating up at 2 meters per second squared. I want to know what is your weight and what is your normal or apparent weight. If you see apparent weight, it's the normal force. Oh, we need to give you a mass. Let's say the mass of this person is 50 kilograms. Okay? So there's a couple things we can look at here. I'm accelerating upwards. What did I say about accelerating upwards? You're going to feel heavier. So I should see the normal be greater than the weight. Let's double check that. The weight will simply be 500 newtons, m times g. My apparent weight, my normal, well, how would I set this up? It would be net force equals, motion is up, so the normal force is up, weight is down. This would be normal minus weight. I'm solving for normal, so let's move weight over. Normal will equal F net plus the weight. Do I have formulas for both of these? I do. MA plus MG. Now what we do a lot of times is this is the same M, so I'll write this out as N equals M times A plus G. And I plug it on in now. N equals 50 times 2 plus 10. And so that equals, the normal force equals 600 newtons. Hey, awesome. It's greater. That's what we expected. All right? Excuse me. Let's try this now. Let's say, excuse me, normal and weight. Let's say you're still moving up, but let's reverse that. Let's now say the acceleration is downwards at 2 meters per second squared. How do I do this? How do I treat this acceleration? Well, what did I say about the direction of motion? This is positive, so normal will be positive, weight will be negative. What do I have to do to the acceleration? I have to make it negative. So I still have the same formula. It's still F net equals normal minus weight. Normal equals F net plus weight. But what do I have to do? Normal equals MA plus MG. Normal equals MA plus G. But how do I plug it in now? It would be, I'm going to still keep this as a 50 kilogram person. It would be 50 times negative 2 plus 10. That's going to be the most difficult thing, is for you to remember the direction of motion is always positive. Anything pointing opposite of that, make it negative. And so this would be 50 times 8, which would equal 400 newtons. So now my apparent weight is less than my real weight. All right? Same thing goes when the elevator is moving down. If I do a quick problem. If I accelerate downwards, move downwards. What if the elevator is going to a lower floor? Again, I'm going to keep my 50 kilogram person here. Same free body diagram. All right. Let's actually continue that problem. Let's say it's A equals 2 meters per second downward. Would I make this negative now? The answer would be no. Down is positive, so this is down, and so that's positive. So let's solve the problem, though. It does change up my net force equation. It's going to be weight minus normal. So how do I do this? It would be normal equals weight minus F net. I add n to this side, subtract F net to that side. Okay? And so now I get normal equals mg minus ma. And so now I get mg minus a. And look what's going to happen. It would be 50 times 10 minus, is it negative? No. Down is positive. A is going down. Minus 2. Guess what? It comes out to 400 newtons again. All right? So hopefully we see a couple trends here. The rest of the problems I'm going to have you to try to do on your own. All right? So main things to remember. Okay? 1, direction of motion is positive. Now, one thing that didn't come up. If the problem doesn't problem doesn't tell you the direction of motion. You pick the direction of motion. All right? You pick. It's not going to be wrong as long as you do the problem correctly, as long as you're consistent with making things positive and negative as you need. So don't be scared by that. Some other trends that you saw: when you accelerate upwards, the normal will be greater than the weight. When you accelerate downwards, the normal will be less than the weight, regardless if the elevator is going up or down. It's all about the acceleration that determines those things. For you to discover would be what happens at constant velocity and what happens if you fall at 9.8 or fall at 10 meters per second squared. What will happen to your normal? What will the normal and weight be at constant velocity? So those are two things you'll discover while practicing some of the problems.